Christine Sutton. If you could see Sandy Brun before she leaves, she'd be very grateful. I'm not sure why she wants to see you, but she'll be glad to tell you about that. Okay, so that is all of the announcements. So we will continue with Professor Daqing Wan's lecture series on Zeta functions of Toric Calabi-Yau hypersurfaces. Thank you.
Okay, so today we'll discuss Newton polygon and its variation. And first, let's review the definition we had yesterday. So we have this Laurent polynomial f. Then we know the zeta function is reduced to the study of the L function, which is we always assume it's regular, delta regular. So the L function is a polynomial of degree d of delta, and we're interested in studying the slope of this eigenvalue. And this slope a rational number in the interval from 0 to 1 plus 1. And so we patch this number, rational number, into a polygon. So for each slope S, there is a horizontal length, horizontal length would be h of S. H of S is exactly the number of those roots where the slope equal to a given S. So basically, if you know the Newton polygon, you know the absolute value, optic absolute value of all of these roots. So we're trying to understand the Newton polygon of this L function. So this notation really means the Newton polygon of the L function, not the Newton polygon of the F. Of course, an F is defined the polynomial over Fp, infinite field. So this lecture also depends on the field, the Fp, prime number P. That's implicitly there. And we know this Newton polygon, it's also from yesterday, has a lower bound called the Hodge polygon. So the Hodge polygon is defined using this Hodge number, Hk, which you find by counting the number of lattice points in k times delta and a prism into a Poincare series, generation series, and the numerator, coefficient numerator gives the Hodge number. So the Hodge polygon will be just, you patch this Hodge number into this polygon, and for each side of slope k, the horizontal length will be Hk. And so the relation between Newton polygon and Hodge polygon is the Newton polygon lies on or above the Hodge polygon, and with the same endpoints. So that give us a lower bound. And for the individual f, then this can be equal or can be greater than that. It's not clear what it would be, and it would be difficult to decide exactly what it is, because the answer, there are many possibilities for the answer, and the answer moves around. Okay, so today we're going to study the variation. How this Newton polygon vary when f vary. And I will study the geometric variation. That means I might fix my field, fix my characteristic P, and let the coefficients vary of that recorder. So I get a family of polynomial, and then I try to understand how this Newton polygon vary as the coefficients vary. Okay, so that's the topic of this lecture. So start with the geometric variation. So given a prime number P, given a particle delta, and given prime number P, then I consider the universal family of all the Laurent polynomial defined over Fp bar. That's very closure of the finite field, such that the polytope is delta and f is delta regular. So I will let f vary in this family. Of course, the first question is whether this family is actually empty or not. And that's not clear because now, if you work with a complex number, of course, then that is non-empty. But if you reduce modular p, then it could be empty. So the first question you can ask, when this parameter space is not empty. So basically, in Batter's lecture, he described this principle A discriminant, and that's a polynomial of the coefficients. And the coefficients are integer, but they could have a common factor. So you put the common factor, what's left is a primitive polynomial. If the prime number p does not divide the common factor of the coefficients, then we reduce modular p, the polynomial is still non-zero, so you are okay, this will be non-empty. So in general, you may have to throw out a few p. If you want to include those p, then the space could be empty. Okay, so it may be interesting to study this actually, the GCD of the coefficients of the A principal, A discriminant in terms of the polytope. Anyway, for us, we are interested in not just a single p, but for most p or for many p, or for p is large, using the description of the in Batter's lecture, then you can easily show this cannot be, at least for p is large, this is not going to be empty. Because as long as p is bigger than the GCD, that be enough, you'll be safe. So, for instance, you can take the p is bigger than d of delta, then this is not empty. The GCD can, maybe bigger than d delta, but we're only interested in the prime factor dividing the GCD. So if the prime factor is bigger than the degree of delta, then you can show this is not empty. All right, so let's take a point in the parameter space. Take a geometric point in this parameter space, and then of course this point has to be rational over some finite extension of fp. Depending on which polynomial you take, you could solve for some fq, which is an finite extension of fp. So fq would, the extension degree would just use the degree of this coefficient. And once you have chosen this fq, then f is defined over fq. So we define this quadratic Newton polygon of the cell function. So this is then defined. Of course, at this point, you can ask, well, there are many choices of fq. If I choose a bigger finite field, then maybe you could ask, quadratic Newton polygon could be different. It turns out that's not the case. This one is well defined. If you choose a different, bigger q, for instance, because I define the quadratic Newton polygon, this is rescaled. This definition is actually independent of the finite field that you take, which contain the coefficients. So this is actually independent of the choice of fq. So really, this is this geometric invariant of this polynomial, arithmetic invariant. Okay, therefore we have given a point, geometric point, on the parameter space, we actually have a Newton polygon that is well defined. And then now, so you let your f vary, the point parameter space vary. Then you can ask how this vary with f, this set of discrete invariants. And to understand that, first, of course, you have to understand how the cohomology vary when the parameter vary. And for that, you can show the relative cohomology which occur in the computation of the L function that depends on the parameter, of course, that is actually locally free in some sense. So locally free, that is true initially over the finite field. Then, of course, you have left, then you have to work with some power series, work with some periodic power series. And then, therefore, you get a notion, what is it called, the Neff crystal. So you have a module, locally free module over this, a lifting of this parameter space, and therefore, you get an F crystal. So whenever you have an F crystal over a parameter space, then for each point of parameter space you have a Newton polygon. You can ask how the Newton polygon vary when your parameter vary. And there's a general structure theorem that is called the Grothendieck specialization theorem, or which is discussed by the Grothendieck-Katz theorem. So by Grothendieck-Katz theorem, then okay. What is this Grothendieck-Katz theorem says? Okay, let's look at all the Newton polygon as F vary over the parameter space. So this will be an infinite set. We have infinite Newton polygon. Actually, the possibility is only finite. So sometimes it's up, sometimes it's down, and it's not clear. You can always compare this to Newton polygon. So the relation between the different Newton polygon may not be simply related by greater or equal. So this greater or equal that give you a partial order, doesn't give you a total order, give you a partial order. So you have this finite set, and there is a partial order. And this Grothendieck-Katz theorem tells you there is a unique initial element, lowest one. Everything lies on or above that. Okay. So there exists a unique initial element with respect to the partial order let's call it greater or equal to. That's a partial relation, partial order, and then there's a unique initial element. And this element is denoted by GMP delta P. Now, what does this mean? This notation suggests it's a generic Newton polygon for delta and P. So this one has nothing to do with the parameter anymore. It only depends on your polytope and the prime number P. Now, why it's called generic? Because it is obtained by most. So there is actually a subset, let's say, in the parameter space. This one is open, dense in here, such that the Newton polygon of F, we know that because that's an initial element, we know this is greater or equal to that. We want to know when they actually equal. If it holds, if and only if F is in this open dense subset. So basically the lowest one which exists, that is obtained by most F, generically. Generically it is at the bottom. So when you go up, then there are fewer and fewer polynomial. The Newton polygon goes up. And therefore this gives you what is called a Newton stratification of the parameter space. You use a Newton polygon, that gives you stratification of total space. So here you have this, this is the lowest one. So this is the lowest one. And Then if you specialize the parameter, it could go up. This could be one of the possibility, for instance. Or if you specialize, of course, when you specialize, it's not going to be monotone in general. So if you specialize a different way, you could get something like this. So there are lots of combinatorics here, and it's very complicated, very interesting to understand how what is this Newton stratification or slope stratification. Of this parameter space. So this is a very complicated problem, for which I will not discuss it anymore. I want to discuss something simpler, where the answer is cleaner, hopefully. So, given an F, we have this Newton polygon, and we have this Hodge polygon, which is a Newton polygon lies above this Hodge polygon. And now, for most of the Newton polygon, they're actually equal. The generic one sits in the middle. And we know we cannot improve here because this holds generically. So this equal generically. So then the question we ask, when we can improve here. If this is equal, then it is equal generically for most F. Therefore, just define a notion called ordinary. So if this generic Newton polygon equal to the Hodge polygon, then we simply says delta is ordinary at P, the prime number P, or P is an ordinary prime, or P is ordinary for delta. Which means this family is generically ordinary. So therefore the question is, which P is ordinary for delta? Given a prime number P, you ask, how do you determine whether P is ordinary? That's possible. That's actually a conjecture, which is I need to discuss. In fact, that is sort of the initial, in the case of a smooth projective hypersurface, that was conjectured by Mazur in 1972 in his paper of the classical smooth projective hypersurface, universal family. Considers the universal family a smooth projective hypersurface. There, of course, he did not exclude any prime, all prime, generically. Now here we work with polytopes. There is a lot more possibility. A lot of combinatorics comes into the picture. Yeah, the smooth projective hypersurface. That was right. Universal family of smooth projective hypersurface of a given degree and then dimension. And even for complete intersection, universal family that is also true. For instance, just look at the class. That may be that's not easy to prove. You can look at either case, just smooth projective Planck curve, universal family. Then the Hasse weight matrix is generically non-zero. Basically, has a full rank G. So the slope, zero part is ordinary. Then because of function equation, the other part has to be ordinary as well. So you're done for curve. Because for curve, you only have two sides. So if you know the slope of zero part is ordinary, the other part is done. But for higher dimension, it's much harder because slope only tells you the first side, then there are many sides. So the middle, higher slope side, that's more difficult. You cannot be recovered by modular P information. Slope of zero side, just the modular P, work with the modular P, that's enough. And you can reform the order of my question, restrict to just the first few sides instead of the whole Newton polygon or Hodge polygon. You can just with the first side, first two sides, first three sides. Sometimes you could have something which is ordinary for the first few sides, but not ordinary for the higher sides. Because you can decompose the problem, cut them into pieces. Yeah, for the universe family, I understand the universe family. Because for a single one, we know we cannot even in general prove for a single prime whether it's ordinary or not. So that was actually one of the initial evidence that this could be, all the prime P could be ordinary. Of course, first in this case, no. Now we have this delta business. Because the total primary space could be empty. So, of course, if total space is empty, then you can assume automatically it is ordinary, so it's okay. Or, if you don't like that convention, let's say you throw out those P for which the total space is empty, which there are only finite many. It doesn't hurt too much. So you can assume, okay, let's say, you can conjecture that this is ordinary for large P. So that we rule out this small prime for which this primary space could be empty. So here's now we understand which prime P is ordinary. So this was indeed a conjecture of Adolphus-Sperber, who studied the exponential sum. Their conjecture is actually more general. They work with the universe family of exponential sum. So this is a sort of a geometric case of their conjecture. They said delta is ordinary for all P. I guess they are assuming this P is sufficiently big. One of their reasons is because the total space could be empty for small P. And I don't know if there's another reason that okay, so anyway, so this is sort of the conjecture. So I want to discuss what one can prove about this conjecture. Yeah? Yeah, right.
But the thing is, it's only empty because of the non-degeneracy condition.
That's right, that's it.
So there is a notion of ordinarity which would work perfectly well, even if, say, it's just non-singular and but not this strong non-degeneracy. You don't have to have strong non-degeneracy to have notion of ordinarity.
You mean instead of consider non-degenerate, you consider this weaker notion of just smooth. But even that can be empty.
That can be empty.
Even that can be empty of small p.
That's empty in the previous
You still have to exclude a finite number of prime. So it doesn't hurt too much there. But of course, so there's really two parts of the question. One is, okay, you consider large p, almost all p. Or you consider all p, including which p is for which your parameter is empty. Well, that's a problem of different nature. Basically, you need to study the GCD of the principal discriminant, the coefficients. So that's a problem different nature. Of course, that's also interesting. And actually, if you just assume your hypersurface is smooth without assuming this stronger regular condition, then it's not clear what is exactly the shape of zeta function. So the cohomology may have a singularity infinity that causes a problem for computation of the beta number.
Did you also say that this Newton Hodge inequality might not hold?
Well, in order for Newton, when you go to Hodge, you have to define what is Newton, what is Hodge.
Yeah.
So for Hodge, you have to define the Hodge number. Of course, if your F is not beta regular, your cohomology may not vanish for the other cohomology, and the beta number may depend not just on your polytope, but actually on the singularity of the nature. So you don't even have a good understanding of this Hodge number. And then for the zeta function, we don't even know how many zeros in the pole. So we don't even know the total length of the problem. So that makes the less well-defined. So that's why we restrict this regular case. Of course, once this is settled, you can move on to your singular case, which is apparently even more interesting and difficult. So so what one can prove? First, we know that delta is ordinary means what? Means generically ordinary. Generically ordinary means if you can find a single f which is ordinary, then you are done. Okay. So that means if you can compute a single L function for given delta, and you can show for that one is ordinary, you'll be done. So the question is, how can you find a single one? Now for general delta, a single one is as difficult as every other one, so there's no way you can do that. But there's one special case you can compute, where is the case delta is a simplex. If delta is a simplex, you just take the special f where only those terms with the vertices occur, all the other coefficients equal to 0. In this case, this polynomial is what I call the diagonal, where you can compute the L function using elementary method, is simply Gauss sum and Jacobi sum, and you can use Stiglberg theorem, which tells you when it is ordinary. And actually that gives you one congruence class. So basically, if delta is simplex, you can prove a weaker result first conjecture. You prove this is ordinary for infinite minimum p with positive density. In the case delta is simplex. Of course, the density, you use a Stiglberg theorem, it's very weak, it's very poor. But still, it gives you something non-trivial information.
So you're saying concluded.
I'm just saying, just for simplex, then you can use the elementary method to prove that you can find a single one for the infinite minimum p, not for all p.
Actually, in this conjecture, can they make that p effective?
Well, you can assume p is greater than degree of delta. First, then if p is greater than degree of delta, then we know that total space is not empty. So no, that may not be enough, but that will start.
For computing, it would be nice to
Sure, I'll get some more explicit and effective condition later. So anyway, so if delta is simplex, then we know a weaker version of this is true. So what if it's not a simplex? If it's not a simplex, then any single one is as difficult as any other one. There's no way one can compute a single example. So in this case, there's no elementary method to approach this problem. But nevertheless, one can show similar results. So there is a positive integer such that if p is congruent to in this residual class, then p is ordinary. So basically, oh, excuse me, no signal. We'll switch.
Nobody else knows how to do this. Dinesh, you know. So the waiter.
Yeah, no, so.
So that's the first result one can say about this conjecture. Of course, then you can ask, what is this D? If D is 1, that would be great. Or even 2 is not bad. It's not clear. I mean, so it will be very interesting to find the best possible D. And in fact, orphan D is 1. Quite often D is just 1. That means that is actually, sometimes D is not 1. It could be. So I'll talk more about this. So in no-dimensional cases, if the dimension of the polytope is 3 or less, then it turns out, yes, this is 1. So then can take D equal to 1. That means for all prime, but maybe we have to remove a few small prime because it could be empty. Okay, I'll just, let's say, let me state it in a different way. So then, P is indeed ordinary. For all P is greater than, let's say, the degree of this polytope. So this would handle all for the case of N3. What do you get? N3, the hypersurface will be 2, dimension will be 2. So this handle all curve and surface, toric curve and surface. Basically, everything behaves very nice. So you can ask then, what about N is 4 or more? And there it turns out this is force. So for each n, actually, there exists n-dimensional delta such that delta is actually not ordinary for many p, for all p in a residue class of some integer, of some d, let's see. So basically, that means this, if dimension is 4 or more, then there are infinite many p with positive density for which the generic Newton polygon lies strictly above the Hodge polygon. Small d? No. Small d is the beta number. Capital D is some integer, positive integer which we know exists, but it's hard to compute. The smallest one.
If 3 is true, then why do you write a conjecture?
Well, that's not my conjecture. The theorem is mine, but the conjecture was not mine.
Yeah, that conjecture should be modified to weaken, right? It came first historically, probably.
That's right. So the conjecture came first, of course. If the theorem came first, they wouldn't have made this conjecture. But actually, at that point, the evidence was quite convincing because in all the cases, there are many examples. And all points to the truth of this conjecture. Of course, most of the time, so you have the universal family of curves, for instance. You have a universal family of hypersurfaces of complete intersections. In all those cases, your D is 1, and it's all prime for all prime. And even if you play with exponential sum, they have a lot of examples with exponential sum. Actually, for exponential sum, that's their conjecture. P is congruent to 1 modulo D for some D, but that D depends on for exponential sum, it's different. So their conjecture is actually for more general for exponential sum, where they do have a congruence class, like P congruent 1 modulo some D. But in the case of geometric case, the D is always 1. So therefore, their conjecture reduced to the case for all prime, not prime, if in the geometric case of zeta function. For L function of exponential sum, you do need this. This is necessary. Okay, so now I want to explain a little bit of idea which goes into the proof of the theorem. As I said, in one case, there's an elementary method you can prove, you can use, which is a case when delta is simplex, where your polynomial only involves the vertices, non-zero term only involves the vertices. That's what I call the local case. So for the purpose of our lecture today, I will state a special case. So first you use, let's say, assume delta is very small, as small as possible. Some people might call it empty particle, or I just call it indecomposable. That means that this delta is very small as possible. There are no lattice points other than the vertices. Okay, so indecomposable means no lattice points which are different from vertices. So all lattice points are vertices. In this case, of course, your polynomial, all term must involve the vertices. So, okay, so you can use elementary method to study. And in this case, one can show if P is congruent to 1 modulo this d of delta, this d of delta is just the base number, the degree of this one. So this is very explicit. If this holds, then delta is ordinary at P. So here, you just, the tool just use simple Gauss sum and plus the Stickelberger. So Gauss sum, in this case, the L function, the roots will be just product of Gauss sum. And Stickelberger theorem tell you the exact the slope of the Gauss sum in terms of the periodic digits of some rational number. And using that, then you can use this very simple elementary result.
So little d is a determinant, or
What?
little d is that?
Little d is it's just, in this case, of simplex, so little d is just the n factorial times the volume of this delta, which is a capital volume matter of this lecture. Or it's really just the determinant of the versus vector. So that's the value of the determinant. Okay, now from this you can already get one corollary, very simple one. Let's say this already tells you if n is less or equal to 2, and suppose delta is decomposable. Of course, in this case, you know you can check this is 1. This you can prove just directly. And so, if d is 1, using that, then delta is ordinary for every p. For p. Okay, so this is a little bit too simple, but it gives you some small, tiny bit of information. So actually, we want to work with something slightly more generous. Okay, I want to work with a slightly stronger result, elementary result. So let's say we start with a simplex. Let's say with the vertices V0, V1, so Vn. So a simplex exact has a number of vertices is just n plus 1. And I assume this is indecomposable, small as possible. And I assume P does not divide d of delta. And in this case, you can check this normal polynomial must be regular. Then I want to know which P is ordinary. And P is ordinary for delta if and only if, how do we term? If and let me just write on the statement. If and only if the degree of the points in the fundamental domain of the lattice 1V0 1AN. So this is a fundamental domain. This is a finite abelian group. And each point, the last point, so let's just draw a two-dimensional, here's a picture. So let's say this is your delta. This line is your delta. So I put it in a higher dimensional space through an origin. This line would be my delta. And then I draw a fundamental domain, put it in a higher dimensional space, delta bar, and I draw a fundamental domain. So I only, instead of looking at all the last points in the cone, I only look at the last points in the fundamental domain. For the two-dimensional case, actually, as the hero was there. So for each lattice point, there's a notion of the degree. In the graded algebra, there's a notion of degree. The degree of the points is stable under multiplication by P. So this finite abelian group, you can multiply by prime number P. So if you multiply a lattice point by P, then you reduce back to the fundamental domain, you get another point. So the degree may have changed. That means the degree, the number of layers, the location of the layer may have changed. So basically, this gives you a necessary sufficient condition for P to be ordinary for this indecomposable family, for the indecomposable case. It basically says the lattice points on each layer must be stable under multiplication by P. So when you apply P acts on these points, then you cannot take one point to the next layer. It has to be stable on the same layer. The degree has to be stable. So basically, the degree of a lattice point here must be equal to the degree of P times U. Of course, we're looking at in the fundamental domain reduction. Now, if you use this stronger version than the previously simpler number one, this gives you a stronger quadrilateral as well. This says, for instance, if you have n is three-dimensional and the delta is indecomposable, then in this case you can show, of course, in this case the degree, the volume may be bigger than 1. The number doesn't have to be 1, but however, you can get this degree stable. Is P stable in the multiplication. So then you can use this lemma. It tells you it's ordinary. P is ordinary. And in fact, you can also get some information for four-dimensional case using this lemma. That will be useful to application to the case of reflexible particle, to the Calabi-Yau case, three-dimensional Calabi-Yau case. Yeah, this is a local theory. This part, everything is done by Gauss sum, statistical programming with combinatorics, lattice points, multiplication by P. So everything is just a finite abelian group, cyclic abelian group. Well, basically, the Stigberg theorem tells you the slope of the Gauss sum. The Gauss sum, there are several roots. So the Gauss sum, the slope actually, it's sort of the sum. It's sort of the average of the several different Gauss sum. So it's not. So that means the slope actually, in general, does not come from a single individual one. You really have to add up the slope for several roots and take the average. That gives the slope. Right. So this really depends on P. I mean, of course, by definition, Newton polynomial we know depends on P, and so P comes into the picture. Prime number P. So it's a relation, not just the combinatorics relation of delta, the prime number, how prime number P relates to delta. That's the arithmetic part.
It's difficult to explain how this
No, it's not technical. That's very clearly explained in the paper which I posted. So this quadro handles the case in 3. For instance, 4, then there are counterexample. But if you assume it's something like beta, like it comes from a piece of the reflexive one, then you can go 1 dimension higher. So that's the case that I will use later on, so I stated this quadro as well. Let's say if it's 4, and delta is decomposable, and assume 0 is a vertex. So in this case, assuming 0 is a vertex, then let's say then there's a unique codimension 1 phase. And that equation would be written in this form, let's see. But in general, that would be a rational number. So I assume this is actually integer. Now that's where we work with polytope, reflex polytope. Each piece will have this property. Exactly. But right now, this is not reflexive yet because this is decomposable. It's just a piece of that. Okay. Now in this case, okay, assume this condition, then you can check again. Delta is ordinary for all p does not divide the degree of delta. Okay, so that's basically the local theory. In fact, the counterexample was already given by the local theory. So for instance, 4 or more, you can actually find the delta for each dimension, where it's indecomposable, where the weight is not stable under p action for infinite many p for open p in a certain congruence class. So that's why. So the counterexample is not hard. I mean, you can find a counterexample. The only case you can find a counterexample is you can compute something. So if you cannot compute it, then you can find a counterexample. If you cannot find a counterexample, that means it could be true. Okay. All right. So I will not discuss counterexample because it's less interesting. I look at the positive results towards this direction. All right, so let's say how do we use this elementary results to prove the general results for delta doesn't have to be decomposable, the big one. So the idea would be what I call decomposition theorem. So we have a delta in the nearest very big. And however, we cannot compute the L function because it's too complicated. We cannot even compute a single L function. However, if our delta is small, it's minimal and decomposable, then we do have an elementary measure that we can try to prove as much as possible, analyze all the situation. So the idea is we understand the small local case, we do not understand the big piece. So if there's a theorem which you cut big delta into small pieces, and you can somehow use information from the local pieces to deduce information about this big family, then you'll be done. Okay. So that's the next topic theorem, which I call the global decomposition theorem. And this section I will discuss one decomposition theorem called collapsing decomposition theorem. Okay. So what is this collapsing decomposition? I draw a picture to describe what it means. So let's say you have a polytope which is very complicated. It's a very big one. And so there are some vertices. Let's say you start with vertex V1. Okay. Now, collapse means, let's say we choose a vertex V1. Choose any of the one. Just choose one. And then you remove this one. You remove this one, this will collapse. So you collapse into something smaller. So collapse some. So this will be a smaller one. This is your total delta. And we remove one vertex. What's left collapse into smaller convex part one. You give delta 1. And then, of course, this two has some boundary intersection. And you use this one. You connect with V1 that gives some other pieces. So this would be your, let's say, your delta 2, that would be your delta 3, and this would be your delta 4. Okay, so this will give you one decomposition, but still, the pieces could still be very complex, still big. So you just continue this procedure to apply to each pieces. So you just continue by induction. Of course, at each stage, there is a choice of the vertex. So if you choose different vertex, the final decomposition could be different. So you can choose the vertex any way you like. So by continue by induction, eventually, then you get decompose delta into indecomposable pieces. If this is done, that's what I call a complete collapsing decomposition. So assuming you do have this complete collapsing decomposition, so be a complete collapsing decomposition. So each delta is actually indecomposable anymore. So at least you can use the local theory to understand each one. Now the theorem says if P is good for each local piece, then it's good for the global piece. So, okay. So if P is ordinary for each of this piece, then P is ordinary for delta. Of course, here maybe I should assume P is greater than D of delta. This problem contains a problem not necessarily because they may have a trouble quoting from this principle indeterminate. So, so let's say suppose each piece delta is the primary space is non-empty. I would think that would imply the total the primary space for the total delta should be non-empty. But it's not clear to me. So maybe people study this principle indeterminate. This should be follow from the construction or the theorem, the description there. So basically, the total primary space is supposed to be much bigger than each primary space for each small delta. Of course, here there's some prime number involved. So if I put this condition, that will be certainly safe. This condition is probably not necessary. Okay, so this provides the connection between local to global. Of course, this is just one. This is not if and only if. Okay, this just suppose that if you use this kind of decomposition, and if each local piece is good, the global piece is good. The converse, I'm not saying the converse. I don't know if the converse is true or not. Probably not true. So now you can already prove the first part of the theorem, which I described before, because for each local piece, we know for piece congruent to those d of delta I, then it's ordinary. So now you just take the greatest common multiple of those denominator d delta I. That'll be enough to give you this congruence class. So collaterally, this merely gives you the collaterally. So theorem A, part 1, follow immediately. And also, theorem A, part 2 means also follow. There are assuming that n is less or equal to 3. If n is less or equal to 3, where was my local number? If n is 3, each thing indecomposable is always ordinary for every p, because in this case degree is p stable. So that handle the case if n is less or equal to 3, then it's always ordinary for all large prime number p.
What's theorem A1?
A1 is the congruence class. Is for let me just put the theorem back. No. Sure, this give an explicit procedure to compute one of the d delta, but the computation you get may not be the best possible. There could have. Yeah, this gives you a bound. The smallest one, it's not clear. Also, there's a choice of the vertex you started. So for different decomposition, you could get different delta. So you can ask, which gives you the best choice. That's very complicated. It's hard to understand. All right, so that gives one decomposition. So later today, my second lecture today, I will discuss specialize a case to the reflexive case and give the application to the Calabi-Yau, general Calabi-Yau hypersurface, where one can actually say more. So these are basically general results for arbitrary delta. If delta is reflexive, then sometimes you can show it's always ordinary in all dimension. And we show you here we can improve from 3 to 4. It's always true. So that one I have to use a different decomposition theory. And then maybe we can discuss this Newton mirror symmetry business, which raised this question under whether this Newton polygon or general Newton polygon has some sort of mirror symmetry property under this mirror of reflex